By the way, how do you think about this paper?
Oh, this paper is actually interesting, but it's mostly mathematical rather than, I think it has interesting applications, is what I believe.
Right, if they have some proofs, right, in the appendix, the
Yes.
paper contents is okay. The math is not heavy.
Yeah.
Just a few pages, it's okay. They
Yeah.
have some proofs for the equivalence, right, of some
Correct.
structures. Yeah.
Correct, Professor. So I'll talk about them towards the end.
Okay, that's
So
good.
yeah. So it was very interesting paper. They have like a lot of practical applications moving forward. Is what.
Okay.
Yeah.
Yeah, they have lots of experiments, right, to show the
Yeah.
experiment to show the application of this model, right, on
Yeah.
the real world data sets. Yeah.
Yeah. Very interesting paper actually.
Okay. By the way, I also want to get feedbacks from students. How is your project? I mean, for the final paper, have you started already or not?
I think I can go first since I'm presenting today.
Okay.
Yeah, we are I think doing good. Our project is that is also using application to audio classification. So we have the data set, we have some starter code as well. We need to figure out some things on how to apply it, how to apply the transformers and other concepts that we want to work on the data set. So
Sounds good. Sounds good. Yeah, my suggestion is you can start earlier. So because the time is limited,
yeah.
and don't wait until the very end and then start working on it. It will be too late, right? So to do research, normally we need to start earlier. Then we have sufficient time to publish the papers and the results, right?
Yeah, absolutely, Professor. We'll start working probably by this weekend. Yeah. So like
Okay.
proper coding and everything will start this week.
Okay. Yeah, I also see the chat from Jingyue, right? You're also implementing the architecture. Okay, that's good. That's good. You're going to work with your teammates, right, to do this. I mean, I think you have a team, right, Jingyue, right? You can partition the tasks, I mean, workload among your team members, and then you can combine them together at the end.
Yeah. Sure. Thank you, Professor.
Yeah, so if you have any question for the project, please also let me know. I mean, I cannot hear your voice actually most of the time. We just discuss the papers. And I host office hours every week, but no one comes, it seems. I don't know why. Anyway, it's okay. Yeah. So please start early, then you can have sufficient time to finish the paper and also do the experiments. Yeah.
And I have a question, Professor, regarding the computing resources. Like
Okay.
if you have a little bit of a model which requires higher computation, then are there any resources that could be provided for us?
So for the course, probably no. The main reason I checked with the department, it seems they don't have sufficient resources for courses, for teaching. So to show your concern, do you have an advisor in UC Davis?
Yeah.
Probably you can check with your advisor to see if if her or his group has any like servers or workstation that can be used for you to run the models. Then you can see if it will work or not. I mean, depending on the size of your data set, probably you need to run with the GPU, right? Sometimes you can check with your advisor to see if there will be any servers available or not. But for this course, we don't have any. I checked with the department. Actually, it seems they don't have the sufficient servers for all the students to use with GPUs. This is the problem. I mean, it's a common problem nowadays for many of the universities. Also, the GPU seems to be hard to buy. I try to buy GPUs for. I mean, you need to try to. I mean, the price is much higher than regular price nowadays. So you can check online on NVIDIA. They have like a 3090. This kind of GPU is very powerful. However, I mean, I can see the chat. Yeah, Google Cloud. Yeah, Google Cloud. They have some like free credits provided for students probably, and you can use a cloud service from Google Cloud, and they will offer you some like a GPU for you to use. I mean, for your project.
Okay. Thank you, Professor.
Yeah, so I think the time is pretty much up. And so today we will discuss another graph neural network paper, and the title is called Equivalent Graph Neural Nets. And the presenter today will be Sai Vivek Petty. And Sai Vivek will help us lead a discussion for this paper. And I can give the time to Sai Vivek, and you can start when you're ready.
Yeah. Good afternoon, everyone. My name is Sai Vivek Petty. I'm a first-year master student in computer science at UC Davis. Today, I'm going to present about E of N equivariant graph neural networks. Now, before we delve deeper into the paper, I wanted to give a little bit of introduction about why graph neural networks. I think the most common answer that you could get is graphs are everywhere. So some practical examples of the graphs in the real world are social networks, which are very common in today's world. And as an example of this is here. And if another interesting application of graphs is in air traffic. There is a nice visualization created by a team which shows how the airplanes in the world travel in a 24-hour time period. So you can assume that in this particular whole graph, this whole image as a graph, where each city can be represented as a node, and it's connecting to different cities as an edge. You can visualize this as a graph. Now, what are other examples of this? These are all trivial, but something that we might not see on a daily basis. We tend to overlook as chemistry. So if you can see all these molecules, all these atoms, and the bonds between them can also be represented as graphs. So that is also an interesting representation of graphs. And apart from that, you can also use them in linguistics, like representing everything in a knowledge graph, sort of a thing, right? So what I'm trying to say is, like, graphs are everywhere, and if we are trying to learn something, because this data structure is very prevalent, and we can generalize it to majority of the data that we have in the world. So what if we are trying to learn something out of this graph data that we have? I think that's where the requirement of graph neural networks comes into picture, right? This is all good. You're saying that we can use graph neural networks and all, but what is the actual problem that we are trying to solve here? Like in supervised machine learning problem, or in a classification problem, essentially we'll say, if given an image of a cat, we're trying to predict whether it is a cat or a dog. Let's say that is a classification task. So that is the kind of a problem, detailed description of a problem that is given. But in terms of graphs, what is that particular problem we're trying to solve? When I started reading about graphs, it's not very clear to me. There is a lot of nomenclature around, but I wasn't able to understand what exactly are we trying to do here, right? So I wanted to explain it with a simple example. For example, if we take this image itself, this knowledge graph, let's say, now let's say there are two people. One is Vivek, myself, and there is Da Vinci. Now, I wanted to ask this question, whether Da Vinci is a good painter or not. Now, there can be Vivek. Let's say this guy here is James. Now, is James also a good painter? We can ask that question as well. Now, how do we answer this question? Now, if we are not now this particular in this particular node is connected to multiple other nodes in the graph, right? So how do we do this? So that's what we will learn in the next slide. So how do we know is Da Vinci a good painter or not? That's what we'll know. So how to solve this problem, right? So there is something called distributed vector representation. What does this mean? Now, if we have solved normal simple machine learning problems, we use something called one-hot encoding, right? So here we have, let's say, an n-dimensional vector. If, let's say, we have n labels in our data set, we can represent it in the form of, in this form. But the thing is, the problem with this kind of representation is there is a possibility that banana is correlated with mango. And for this, the problem with this kind of representation is that it is not able to capture this kind of correlation between the both, right? So that's where distributed vector representation comes into picture. So in here, each vector each vector that we see is kind of distributed across, and it kind of has this contextual information from other vectors in the data set. From here, I think you'll be able to understand. Essentially, if I apply the same concept to the previous problem, like is Da Vinci a good painter? Now, from the contextual information from other nodes, let's say he painted Mona Lisa. So, and Vivek haven't painted anything in his life. So you can, if at all we are aggregating this contextual information to our vector representation of each node, we can say from this vector representation with the contextual information from others, we can answer that question whether a particular thing is right or not, if Sai Vivek or if Da Vinci is a good painter or not. So the answer is yes, yeah, Da Vinci is a good painter because he has painted Mona Lisa and many others. Now, coming to the next thing, this is all good, but how does it work and like what is the general graph neural network pipeline, right? Now let's imagine there is a graph with nodes from A till F, and we initialized them with some random vector representations of random distributed vector representations. This is how it's going to look like. And we'll apply a GNN. We'll look into what's there in the GNN process, and after that, all of these individual vectors we have here. For example, if we take node C, this is the vector representation of node C, and it will by applying a graph neural network, it will convert this particular node vector representation into another similar space vector, similar dimensional vector by passing through multiple layers and aggregating the information from multiple other nodes in the graph in a message passing manner. And after the output, after we got the output, we will do a task specific stuff, or task specific. I'll define what kind of task that we can do using graph neural networks, but this is a typical representation of graph neural network pipeline. So there will be an initial set of graphs, initial set of nodes with there will be an initial graph which has a set of nodes and edges. And each node will be represented with a specific vector which defines its properties of that particular node. And we apply a set of transformations on top of that node, which will convert this node into something different than the initial. And that vector, that final vector represents your data better because it gets that contextual information from the intermediary layers that we have. So as I've said, like if we want to take a deeper look into what's happening inside that GNN layer as a box, now let's assume we are trying to figure out what is the state. We are trying to update the state of F from a time t equals to 0 to t equals to 1. Let's say we are trying to figure out what's the, sorry about that. We're trying to figure out from t equals to 0 to 2 equals to 1 how the node values of F are changing. Now D and E have certain vector representations similar to F. Now we'll apply a function on top of the edge that is connecting in between D and F. That will be this, and we'll prepare this particular edge, and the information that is flowing from D to F is called the message, and the whole step is called the message preparation step. And similarly for F, we'll get information from D, and we'll also get information from E. So we'll summarize all the informations from D and E from F, and we'll apply another transformation in this process, and we'll update the whole value of this particular vector at a timestamp t equals to 0. And in the next state, by applying this transformation, let's say that state is t equals to 1, it will get converted into this particular state. Now I've shown you here an interesting this thing, but what is it actually doing? Like what is the transformation that you are performing by getting these messages from all the other nodes in your graph, right? So that's what we'll see next. So now if I'm saying, let's say HTN in, let's say at a time t, we are trying to figure out what is the vector representation of that particular node F. So it is essentially a transformation on top of this current state ht minus 1. And we're applying a function on top of all the messages that we are getting from other things, right? So one thing to remember here is like the immediate next question is like, what is this function and what does it do, right? F of t can be a nonlinear function or a linear function which is domain specific. For example, if at all we are working on graphs or graphs of images, we can think of this ft function as a convolution function. If at all we're working on something else, this function can be something else. But one thing that ft should be following is it should be permutation invariant. It's all good, but what does permutation invariance actually mean? To explain it in a simple manner, let's say there is a vector representation of 10 numbers, 1 to 10. Now, if you apply a max function on top of this vector of 1 to 10, you'll get a value, let's say 10. And this 10 is independent of where it is in the vector, right? So that means no matter how many permutations of the vector inside you do, you will eventually end up with the same result. So that's what is meant by permutation invariance, right? So graph neural networks, one basic condition that it should follow is there should be permutation invariant. It should not be dependent on the way in which you represent your graphs. I hope that is clear. Now, so another problem I faced when I was trying to understand graph neural networks is in a neural network architecture, we can assume that there is a neuron in one layer and there will be other neurons in the other layers, and you propagate forward, right? So that's how it happens in a conventional neural network architecture. But in graph neural networks, it is a little bit different. It propagates with time. For example, at time t0, we have a certain vector representation. And at time t equals to 1, you apply that function that we spoke about earlier to all the nodes in the graph, and you will get into a higher into the next layer, and that layer we call it as t equals to 1 layer, let's say. So the time gap between these two is nothing but your effective sampling time. And as the time progresses, your vector representation of each node will get transformed into something different, right? Now, one immediate problem that we can see is like, if it is not like a conventional network, like how do I know where to stop? What is the condition when I terminate the time, right? So there are two things to note here. In graph neural networks, the time variable or the number of layers is also a hyperparameter that we need to input. One other method, like how do we know when do we stop? Like what is the convergence rule for this network? If we ask that question, we can answer this by in two ways. So imagine this network in here is trying to predict a binary classification variable, like as I've explained it before, is a particular person a good painter or not? Let's say we are trying to ask that question. Now, let's say for all of these nodes, let's say each person in this node represent a painter and their relation with some other vectors. Now it's a binary classification. We know whether C is if we already know whether C is a good painter or not, we can apply an MLP layer on top of it and try to predict using the sigmoid function. We'll be able to know whether this particular person is a good painter or not. So that's essentially like a node classification that we can do, right? And from this, we can also get the error here. Like once we have entered into the classification world, we can define different types of errors that are required. I can define an error as binary cross entropy or any other types of errors that we want. And from that error, we'll be able to know whether the model is converging properly or not, right? So what are the different types of tasks we have? What are the different things that we can do with graph neural networks? So one thing is node selection, and another thing is node classification, and third thing is graph classification. I think these terms are self-explanatory. So I've already given an example for node classification. So these are the different types of tasks that we can perform. If you remember previously, I was talking about, sorry. If you remember, I was previously talking about the last step in the GNN pipeline is the task-specific stuff. So this is what I meant by task-specific stuff. So depending upon what is the task that you're doing, your output variable or your error minimization depends on that. Now, in summary, if I wanted to put everything into a simple equations, I can say Mij is message between the ith node and jth node, where I is, you can imagine it as a central node, and j are all other nodes except the center node, and you're getting information from all these other nodes, right? So let's say L is the state vector that represents the time. So and phi of E is nothing but a function, an equivariant function that you're applying on top of on top of this particular state. As I said, that function can be anything, and Aij is the edge information between these nodes. And how do I summarize the value of Mi? Mi equals to sigma of j belongs to n of I. This n of I in here means the neighborhood information. If there is a node and it has only first connected nodes, if you are taking the information only from the first nearest connected nodes, we can represent that as the neighborhood information. And we are just summing up all the messages from this particular neighborhood only. And whenever we are computing the next iteration of that particular node embedding, that is HL of 1 of that particular ith node, it will be given by a function of phi of h. And here it takes the information of the current node information and the message that it got from all other nodes, and it will transform the current hi vector into the next vector. So essentially, if I want to summarize what's happening here, it actually is taking the knowledge of whatever it has so far now, plus it is also getting the information from contextual information from other nodes, and it is updating its vector hi of I. So that is essentially what GNNs are doing, right? Now this is all good, but GNNs also have certain problems. We'll discuss about it moving forward. Again, I want to iterate one thing that GNNs have to be permutation invariant, right? Yeah. Now let's shift gears and discuss about some basic concepts to understand E of n equivariant neural networks. So to understand that, first let's understand what equivariance actually means, right? Equivariance can be in a simple term. Let's say there is a phi is a function that is working on x space, and phi y is a function that is working on phi ways on y space. If at all there exists a function that converts the convolution or the function that you're applying will not affect the latent representation, then it is called equivariant. Let me explain what it means in a very simple manner. So first, let's talk about something called translation equivariance. So CNNs do have let's talk about in the specific case of convolution neural networks where it has translation equivariance. What does it mean by translation equivariance? So for example, let's say we have an image of gecko. Sorry. And let's say we have an image of gecko. And let's say first we are translating this image of gecko towards, we are shifting it right by some pixels. And after shifting the pixels, let's say we apply the convolution, the resulting output is this. Now, if you apply the convolution step and the translation, still the output remains the same. So that's essentially what equivariance means, right? So the order of operations doesn't matter. The end result should be the same. Like first you translate and then apply your CNN, it gives the same result as first you apply the CNN and then translation. So this is a very important concept for understanding, to understand this whole paper. So I'll take a pause and ask any questions if anyone has.
Are there any conditions on phi x and phi y, perhaps the relationship between phi x and phi y, for equivariance to hold, or can they be any transformations?
They can be any transformations. So there are three different types of equivariance, that three different types of transformation that we'll look at. I'll talk about it in the next slide, but they should be able to take any transformation.
I see. Thank you.
Yeah. Okay. Now, moving forward, I said there are different types of transformations that you can do. So one type of transformation is translation, one type of transformation is rotation, and one type of transformation is permutation. So there are three major types of transformations that it should hold to call it as a E of n equivariant. So what does E of n equivariant actually means? And first of all, let me even talk about what does rotation equivariance means, right? So what does rotation equivariance mean? Similar to what the translation that we have done before, if we actually rotate the image and apply all the transformations, and we apply the function and then rotate the image, they should give the same output. That's what rotation equivariance means. So this particular rotation equivariance is very, very important in many of the upcoming domains, in like quantum chemistry or molecular simulations. Why? Because the bonds or the representation of any molecule in three-dimensional space, with rotating that particular bond, it should not change, it should not affect the output of that particular simulation, because H2O written in one way or the other way is the same molecule and it's independent of rotation. So rotation equivariance is very, very important concept to preserve. So like if at all there is a method that kind of ensembles all three things in their model, then it's called E of an equivariant. What does E means? E is nothing but Euclidean spaces. Think of Euclidean spaces as a coordinate space, and N is the dimensionality of that particular space. In paper, there are. I also got confused initially when they interchangeably use E of 3 and E of n. Later, I got to know that E of 3 is basically a three-dimensional space. Many of the works that are done prior to this paperwork are primarily concerned on three-dimensional workings, on achieving three-dimensional equivariance. Sorry. On achieving three-dimensional equivariance, but the paper in this paper, whatever they have implemented, they are able to extend it into n dimensions, which is they've done it in a very smart manner. We'll see how. Now, yeah. So I said in previously we saw translation equivariance in CNN. CNNs are translation equivariant, but they're not rotational equivariant. You can see, right, like, because if the image is rotating, the output of this output of the convolution is actually changing. So CNNs are not rotation invariant. So there are a lot of research work which is going on in that thing. So there is one particular paper which achieved this kind of rotational invariance by applying some harmonics equations. But I just wanted to show this to explain that there is this rotation equivariance problem in CNNs. Now, if we wanted to see how the authors in this paper extracted or used this equivariance, how are they achieving this equivariance in? Let's see how they achieved this equivariance in this paper. So, if you remember previously, I was talking about a graph neural network, and these three are the primary equations for graph neural network. So their method is a very simple method, but very powerful in terms of output. So what they have done is they have included positional embedding for each node, which we can call it as XL. So that's the positional vector. Like here, you can think of it as the position of x1 and this as the position of x2 in some Euclidean space. And you are now this whole, previously it was this. Now they're transforming this into this, right? So now that they just added the norm or let's say Euclidean distance between the 2 points into the message passing system, right? So this is one additional parameter that they're giving to this phi function, and again emphasizing and reiterating on what phi is. It is essentially, it can be any nonlinear transformation or a function that you could apply on these input parameters. So one thing that we are adding here is this norm, right? And how are they updating this xi? So using this simple equation in here, they're updating the value of xi as well in the future iterations, for the future iterations, right? You can think of it as a simple distance equations, absolute distance between these two, and you're multiplying it with another transformation function phi x, which will result in a scalar value, and Mij is also a scalar value. So this whole thing will result in one positional value for xi. So and the next two steps, as I said, like these last two steps where we collect we collect messages from the neighborhood of this particular node. Let's say, for example, we are considering the node x2. So the neighborhood of x2 or the node h2 will be h1, h4, and h3. We'll get information from these particular nodes, and we are just summing up this information. And the last step is also the same. HIL of phi h. This is essentially the transformation on top of the current node vector and the message, right? Message information. So essentially, there are two major things that they have done. They have just included this norm in the equation, and they've added an update rule for xi of l. Now, I want to convince that it follows all three three things that I've spoke about. For it to be E of n equivariant, it has to be translational and rotation and translation, rotation, and the last one is permutation. Yeah, permutation invariant. So I'll try and convince that it is that. So one thing that we can so we can go over the detailed proof towards the end if time permits. But one thing that I told earlier was it is graph neural networks are permutationally invariant, right? So this whole method is a simple extension of graph neural networks. So in terminology, by using induction method, we can prove that it is if we can prove that it is permutation invariant. And similarly, if I wanted to talk about translation invariance, now one thing that I can clearly say, because you're just taking the absolute difference vectors between the vectors, so it ensures that we are maintaining the translation property of a GNN, right? Graph neural network. So for proving it is rotation invariant, we can actually so this is this rotation equivariant function. So we just take orthogonal matrix Q, and we apply this function to XL plus 1, and we apply this equivariant graph convolution layer to QX plus G comma HL. It will result in in the same thing as what we are trying to say. We'll see the why it is rotationally invariant towards the end. But what I want all of you to take away from this is whatever method that they have done, they achieved the E of n equivariance. That means in Euclidean spaces of n dimensionality, they are equivariant with rotation, translation, and permutation. So this is a very powerful thing if we in molecular chemistry and other domains, right? Now they've also provided one more equation for vector extension. So it's just like if at all each of these nodes are moving with a specific velocities. So these things will be specifically useful for n-body simulations, where particle simulations, where if at all the particle is moving with a particular velocity, that should not mean the system as a whole is changing. You can think of it like in a three-dimensional space. If you have a particular particle and it is moving with a certain velocity, it is because the relative position because the position of the thing is changing, it is possible to think that it's not equivariant. But since we are just using this relative vectors, it's mostly invariant with all these. And this simple vector extension, it's like, well, you can think of this vector v as vi as velocity, and so this is a nice extension to simulate particle, how do particles interact in a three-dimensional or n-dimensional space, right? Now let's talk about comparison over different works that there are in this field. So here they have provided different implementations. We have the original graph neural networks. The graph neural networks are not non-equivariant. They are only permutation invariant, but they are not rotation invariants. And rotation equivariance is like a very important concept, because if you want to simulate like molecules or the interaction between the molecules, it is very important to have this permutation invariance, right? So similarly, we have a radial field, which is also E of n equivariant, but the problem with this particular approach is when you are scaling it to higher dimension, it is more computationally expensive when compared to the EGNN approach, right? And similarly, we have TF1N, which I think uses something called spherical harmonics. So one way to achieve this, I think if you have read the paper, you will hear the word spherical harmonics twice or thrice. What this essentially means in a very simple or niche manner is, think of, we are applying the functions on top of a sphere. Since we are representing our entire vector space as a graph, so it is kind of rotation invariant flows. So it doesn't really matter in which direction you turn the sphere. It will be kind of rotation invariant, is what spherical harmonics mean. And there is another thing called Shinet. And finally, we have our EGNN, which is also E of n equivariant, right? So here they have three major things. You can see like what is, so they're essentially showing what is the message passing step in the graph neural network, how it comes and how it aggregates this information from all the different edges, from all the different nodes, and finally the node update step. How is it happening? So they put all these things in here. Now let's talk about experiments. They have done some pretty interesting experiments, I would say, and I think these experiments will allow you to think that whatever they have done is pretty novel and interesting for many of the future works, right? So first thing is n-body simulations. So what does this n-body simulation actually mean, right? Let's say we have in here, they have taken 5 particles. Now, essentially what we are trying to do is, given some dynamics in the system, given some, let's say, some physical properties of that particular system, we are trying to predict what's the particular trajectory of these particles given with the interactions between all these particles. So essentially what we are trying to do is at a certain point in time, we are trying to simulate, we are trying to predict where this particle is going to be at a next time t+1. So they have compared this particular thing with many methods that they have already shown before. One is a linear model, SC3 transformer, tensor field network, radial field, and EGNN. And you can clearly see the mean squared error in EGNN is the least. So It's computationally less expensive, but it's able to generalize the data in a very good manner. And here, if you see the graph, as the training samples increase, right? As the training sample increases, the mean squared error is decreasing, but even at a lower sample space, we are able to see that it performs better than radial field and graph neural networks, right? It's because of the inherent inductive bias that we're assuming about the vector spaces, about the symmetries in the system. Now, moving forward, the second application. This is also a very interesting application, and this experiment kind of sums up why their work is very interesting and novel. So imagine, let's say this is a graph of, or let's say these are the 4 molecules with bonds between them. Now, if they are of similar molecules, let's say these are all carbon atoms with different isotopes, isotopic information, and let's say you're encoding it with something, and after encoding, if at all you're trying to decode whether like if at all you give a parameter, if at all you give a question. So this is essentially a generative model from here, right? If at all you said like if at all these 4 molecules are there in the system, how do they interact? If I ask that question, it will be a very difficult question for it to answer. Like how does this bond form? Will it form the bond with this or this or this or this? Like that's a very difficult question to answer, because almost all the things are very similar, right? So that's where this particular their method EGNN works very well, because of the inductive bias that they're giving at the front. Because if you remember, here they're giving a Gaussian noise as an input, which can kind of differentiate between each of these nodes, and from there you could actually be able to decode in a very less number of with very small data as well, right? And think of this noise is being implemented inducted in the initial step of the EGNN itself, where I told you about the parameter xi and stuff, right? So that xi positional embedding, you can think of it as a normal distribution, right? So this kind of sums up, right, like why this EGNN has a very good thing in the future, right? Now, if we see the results of this as expected, as you can see, if we can think of it as a probability estimate, which is the F1 score. If we look at this graph, now even when the value is less, even then the EGNNs are able to perform better because of that inductive bias that we are inputting into the system. And you see they're actually if they measure multiple metrics, they're able to perform very well, right? Okay. Now, coming to the final system. So this is a molecular interacting system where they're trying to predict what are the values of different molecular properties, like alpha, delta E, epsilon, homo. These are different molecular properties, and when they are trying to predict it using E of an equivariant neural networks, they have very good representation, even though they might not be the best in everything, but they're able to generalize it in a very well manner, right? So that's about the different experiments that they have conducted. Now coming to the problems, if you see one problem that I have noticed, right? So even though we said like the error is minimal when compared to many other models, but it's still not the absolute best. So there is still work that needs to be done. If there is something called TimeNet, which is actually performing better than EGNN, right? And if you look at this forward times here, we have models like GNN and radial field, which take a relatively lesser forward time when compared to EGNN, right? So that's kind of if you think time as a very important metric in your system, so because of the additional little time it takes to converge, let's say, for getting this error, it is taking a little bit more time when compared to the other things, right? And one other problem that I found is while they're describing the data sets, they used I don't know, while saying, they said like 1.00 notation. The data said, I thought, they could have done better with their data set descriptions. Any questions? Sorry. Okay. Now, what kind of future work is involved in this, right? So I said because see, E of n equivariance means in n-dimensional Euclidean spaces, these models will be translation, rotational, and permutation invariant. That is very strong concept, because many of the systems we know in the world are kind of follow this symmetry. So it's very if at all these models, there can be very interesting applications of this in molecular chemistry, in machine learning domain, in quantum chemistry, or even you can think of it in terms of air traffic, predicting what are the appropriate number of what are the appropriate number of stops that are there in a map. So there are very interesting applications that could be done using this, but majorly I think in particle simulation and in molecular quantum chemistry, or in chemistry, it has very wide applications. Yeah, thank you. I'll take some questions now, and I think I'm out of the 15 minutes time that was given to me. So yeah, so let me take some questions now, and then let's see what we can do towards the end.
I have a question regarding the update rule that we have for x's here. So if we think of x's semantically as the position of nodes in an n-dimensional Euclidean space, so why should it have an update rule if it semantically means the position?
So
why should we even update the x's if x means the position of a node?
Yeah. So as I said, this phi of x, this particular node can also be time variant, right? So it's possible that it has certain velocity and it is moving, right, in the Euclidean space. So how do you capture those things? So if at all it has like no velocity at all, it essentially will become zero. This whole value will become zero, and xi L plus 1 will be equals to xi. So there's no harm in doing it. But if at all it is changing the relative distance, then there is a requirement for that. Is what I've assumed, at least.
So like should there be a velocity component in the update rule? I mean, I can't see any velocity component in the update rule for x's. Oh, here, okay, fine. Yeah. All right, thanks.
Any other questions? Okay.
Yeah, any more questions?
So the experiments in this paper were done on graphs of relatively small size in terms of the number of nodes.
That is the thing that I was talking about. The dataset description is not very clear. They said they have done it on 1.00. I didn't understand what it actually meant. Like
I think they use period in place of comma to denote thousands. Like 50.000 is actually 50,000.
Yeah, that I think that's the I think it should be 50,000. If at all it is 50,000, even though if it is 50,000, it's not very it's not a very big data set. It's like still a minimal data set, but these interactions are actually very complex interactions. So I think whatever they have done is okay for now.
And 50,000 is describing the number of data points, essentially, right? Like the number of graphs that they apply the network to. But within each graph, for the molecular interactions, I think it was less than like 30 nodes per atom. For the other experiments, the graphs were also pretty small. I think there was like a somewhere between 12 and 20 nodes per graph. So do you have any intuition on how this would scale with increasing number of nodes rather than increasing dimensionality?
That's a very interesting question. I don't know if it would scale as good as they claim for the increasing number of nodes in the system. But from the equations whichever they have derived, I think it shouldn't be a problem for extending it to multiple number. And if you actually take a look at all the graph neural network equations, they're kind of very similar with small changes. So if at all if at all one is able to scale with large data, I'm assuming this shouldn't have a problem with scaling large data. But I don't know whether it will work properly or not yet.
Yeah, that would be my guess too. I mean, it seemed like, especially for the molecular properties prediction, there's only so many different molecules you can have with less than 30 atoms. And I mean, it's a lot, but it's not representative of the entire space of molecules by a long shot. So yeah, I was curious whether the experiments are kind of like representative of actual practical applications for graph neural networks, or if they're kind of toy in the sense that the graphs themselves are very small. But yeah, I mean, obviously that's not necessarily within the scope of just this paper. So
yeah, so I think this paper is like an introductory paper. They have also done something in recent years. We've read something called E of normalizing flows. So I think they are working on something with more data or something. So I think they're working on it. And one other interesting application of this is in drug discovery. Like if we model these molecules as let's say we are trying to predict whether this molecule can cure cancer or can affect these cancerous cells. Now, rather than experimenting it with experimenting with each and every combination, if we have some model like this that can actually filter out a lot of combinations and will leave us only with certain set of smaller samples, which will ensure which will make the drug discovery process much easier, right? So that is also another interesting application, for it. I just wanted to say about it. Any more questions?
I have a question about the like the invariant, like the equivariant like slide where like they like you showed about like just before the like proof slide. Yeah, like this one or just like the previous one, so whatever. So these size this snap size phi, right? Phi E and phi H, these are neural networks, right?
This can be any functions. That's what this can be a neural network. This can be any nonlinear transformation function. This can be anything that is domain specific.
Okay. So my question is, like, they only add this, like the square distances between the nodes, and then they claim that it makes the like model like equivariant, like intuitively, because these are like equivariant. Because if you translate, the distances don't change. If you rotate, these distances don't change. However, like I don't understand exactly like why adding this intuitively, not like I see the mathematical proof, but like why would intuitively that make it equivariant, where like the old version is not, actually, because old version like doesn't have anything for these parameters. So we are just like adding additional parameters to the network and say that this makes it equivariant.
Yes. So yeah, I also had this question when I was reading the paper, like how adding just one term is making it equivariant, right? So one thing that I understood is the graph neural networks are permutationally equivariant, but they're not rotation equivariant. You can think of it as I can give you an example, right? Let's take an image, right? So if you take an image and represent it as pixels, a grid of pixels, and you can assume that each grid is kind of a node in a graph, and all the adjacent items as the other nodes. Now by rotating by rotating this graph, essentially I think we've already seen that in the above explanation that I've shown for the CNNs not being very rotational invariant, right? So the way I convinced myself is that because they are rotationally invariant, by adding this additional term into the equation process, so that essentially will make it rotationally sorry, those are not rotationally invariant, but this will make it rotationally invariant because it is taking the absolute distances between the nodes as a parameter inside it. If you ask me why is it even working, honestly, because we need to know what this equation phi is actually doing, but in the entire paper they haven't given any exact function of phi. If they had given that such function, I would have tried and explained it using that, but this is how I convinced myself that the GNNs are not rotationally invariant, but EGNNs are rotationally invariant because of this one additional parameter that they're adding.
Intuitively, it seems like GNNs should be rotationally equivalent because they have no information about the x's. They have no information about the position of the nodes in the n-dimensional space, whereas this model has. So intuitively, it seems like this model should be rotationally sensitive to the subject, but it's vice versa. It's the opposite.
Vice versa. Yeah. I also see that's what, right? Like if you have a graph, it makes sense. Like if at all you're mentioning a graph in a in form of adjacency matrices, it's how is it not it's very hard to assume that it's not rotation equivalent, but when you actually do all the steps, it is kind of becoming a rotationally a variant thing. So whatever they have done, they're claiming it to be rotation invariant by adding this particular thing, and that kind of is also proved. Like, so one way to convince yourself is using this particular thing. Like think of it as an image, like if at all you're rotating, it should not affect the convolution step, right? So it makes no sense, right? So why? So this kind of can give you an intuition that even though if you represent these graphs in this format, they will be rotationally variant, right? Logically speaking, with our like regular intuition, common sense, we'll feel that this is not rotationally variant, but they are rotationally variant, and it's been proven. So I think we can convince ourselves that the GNNs are also rotationally variant, and whatever they have done has included this rotational invariance concept into the system.
Maybe I need to spend a little more time on looking at the proof and then trying to understand like what makes it just like also mathematically like logical. Yeah, thank you, but I thank you for the explanation.
I'm sorry, I'm not able to hear your question properly.
Oh, thank you for the explanation. I think I need to spend a little more time on just like reading the proof and then just trying to understand like, yeah, what exactly is happening, and like how can they like how mathematically it's proven that like it's the equivalent, the equivariances, like yeah, ensured. Thank you.
Okay. Any more questions?
Yeah, any more questions from the students? Okay, so if there's no question, then probably that's it for today. I mean, let's thank the speaker. Thank you so much, Vivek.
Yeah, thank you all.
And so also a reminder, I sent you an email last on Monday, right? So for the project, my suggestion is you can start the project as early as possible, so you don't need to rush at the very end. As for the machine for the GPUs, I just sent an application to Google Cloud, and I'm still waiting for the response. Once they respond, I mean, if they can provide us with some credits for GPU usage with Google Cloud, I will also send you an email, I mean, to let you know how to access the GPU service from Google as well. And thanks so much, Vivek, and the talk is very good. Thanks.
Thank you so much. Have a good day, everyone.
You too. Have a good day.
Thank you so much. Bye.
Hi, Professor.
Yeah, sure.
I'm the next presenter. I was wondering that all I need to do before Monday is to send the slides by Sunday at 3 p.m. Is that correct?
Yes, you send the slides to the TA, and then the TA will help you post the slides online.
Okay, I see. Okay, and also one is like related to the final project, because my focus is to utilize one of the transformer model on a visualization task. So is it okay that I don't retrain the network itself?
If you use a transformer as an encoder, I assume you probably have to train it, right? Because right now the transformer is pre-trained on natural language processing task or on vision task, right? I'm not sure if we have any transformer for graph or not.
Yeah, actually, the one I was referencing to, the authors provided their pre-trained model.
Okay, so I don't know how to say it, right? So your project is focused on visualization, right?
Yes.
Then I'm considering the connection to deep learning, right? Because I mean, for the paper, if you only do visualization, then even though you use a deep learning model, right? I mean, so I hope you can learn something to play with deep learning first, right? I mean, so probably you can try to train a model by yourself first, and then to do the visualization state. And then you can learn something more, right? Because if you do something, then you can learn deeper, right? I mean, if you just get a pre-trained model and just access the embedding vectors from the model directly and then do the visualization, then your workload is still about visualization, right? You don't have much experience about deep learning actually. So I don't know how to say, right? So you know what I mean, right? And
Mhm.
depending on your time, if you have time, then I don't know to suggest that you can try to train something by yourself, then to see how it works, right? And then further do the visualization. Then you can have
Okay.
more experiences. I mean, to play with deep learning, right? Yeah.
See, yeah, because my project is about to explain the graph representation, and and actually I was also going to use the same exact data set. So I saw them provide that pre-trained model already. So I was wondering that if I could just use that directly, but I will definitely try to train it myself if if I don't if I eventually don't have time or have problem implementing it, I will just specify I was using the pre-trained model in the paper.
Okay. Yeah, my suggestion, you can try to play with. I mean, you will have more fun by trying a model out instead of just the visualizations. You know.
Oh, and also, if is it possible that because I also have a private data set, and it has a more semantic meaning other than the public data sets. So, but it's not public. So, is it okay that I just describe that data set, but instead of like providing any data, like actual data itself?
You mean you have a private data set, right, in your hand, right?
Yeah. Yes.
Yeah, then you can use your data set. I mean, then you can provide some basic description for the data set and also some basic statistics, like the number of nodes or the size and so forth, right? And all the density of the graph and so forth, right? And you don't need to link the data set to us. Then and you can provide some basic information for data set instead.
Okay, I see. Thank you.
Okay, anytime.